Alright, so we are going to actually cover two topics in one here. The two topics that seem to crop up in the reflections from this week that were most confusing was step 6 of glycolysis, that 2-for-1 step, where we get an oxidation and a phosphorylation. So we'll start off talking about that. And then we're going to switch gears pretty radically and cover the second topic, which was the PDC, the pyruvate dehydrogenase complex, and what goes on in those 5 steps converting pyruvate into acetyl-CoA. I'm going to cover the PDC the way that I expect you to know it for the exam, so we'll leave out the enzyme names and focus really on the concepts and the chemistry that's occurring in that complex. But first, let's talk about step 6 of glycolysis. So I'm not going to go through the slide itself, but by bringing up the slide where step 6 was covered in the lecture, I want you to pay attention with what we're starting with and what we end with. We're starting with GAP, glyceraldehyde 3-phosphate. We have NAD, ready to accept electrons, and we have the phosphate group we're going to be adding. And we end with 1,3-BPG, 1,3-bisphosphoglycerate. We have reduced NAD, and the phosphate has now been added to the substrate. I want you to also notice that nothing happens to carbon 2 or carbon 3 at all in this process. You see how the bottom of GAP remains the same bottom of BPG? All that is affected is carbon 1. So as I go through the sketching of this, I'm going to represent the bottom half of GAP as an R group, just to symbolize that nothing's really changing there, so we can focus on the chemistry that's occurring on carbon 1. So let's go ahead and do that. So as I've just said, I'm going to say that we have an R group here, and we have a carbon linked to a proton and a double bonded oxygen. I'm going to leave NAD off to the side because we really don't need it in the chemistry itself, and I'm going to add to this reaction our inorganic phosphate group. The first thing that happens is a dehydration. Now this isn't considered a dehydration reaction, but we do have a dehydration where the hydroxyl group of the phosphate group and the proton from GAP come together to create water. So water is released. And because water is released, let's go ahead and get rid of those atoms from our substrate. And I'll put that plus back. Additionally, we have stripped this carbon of some electrons. And when NAD accepts electrons, it's going to accept protons as well. So NAD goes to NADH plus H. It is now in its reduced form. And the reason why we often use the term oxidized when we talk about something that lost its electrons is because this has been given a single bonded oxygen in place of the electrons that were stolen. And that oxygen is negatively charged because it's only engaged in one bond. So what we have here is we have 4 bonds now around the carbon, 1, 2, 3, and the 4th for the oxygen that we added due to oxidation. The oxygen itself, though, remains unsatisfied because oxygen is supposed to have 2 bonds, and this oxygen only has 1. That's why the oxygen is negatively charged. It has an unpaired valence electron. It's ready for another covalent bond. If we come over here to the phosphate group, we see that we stole from it its hydroxyl group. Phosphates, or phosphorus atoms, are supposed to have 5 bonds, and this one has 1, 2, 3, 4 bonds, with the 5th bond unsatisfied because we have taken away that hydroxyl. So we have an unsatisfied oxygen that's waiting to make another bond. We have an unsatisfied phosphorus, which is waiting to make another bond. And those two simply come together. And so we have, I'm going to get that water out of the way now. We have that oxygen make a bond with the phosphate. And now the phosphate, the phosphorus, has 1, 2, 3, 4, 5 bonds. It is satisfied. The oxygen has 1, 2 bonds. It is satisfied. And carbon has 1, 2, 3, 4 bonds. It is satisfied. Along the way, we lost a water, and we reduced NAD to NADH plus H. So this reaction is a 2-for-1 reaction. We get an oxidation of the GAP. We get the reduction of NAD, and we also get a phosphorylation because we add an inorganic phosphate group to GAP, creating 1,3-bisphosphoglycerate. What's powering this energy is the delta G of the redox reaction, and the delta G of the redox reaction allows us to add the phosphate group without having to burn an ATP. So that's pretty much what we have as this reaction. If I bring the slide back up, you see that here is that hydrogen, here is the hydroxyl group. They are what leave as water. The double bonded oxygen remains untouched, just as it did in the diagram I drew for you. A new oxygen has been added that wasn't there before. That's the oxygen we added as the oxidation reaction. And that is the oxygen that's bridging carbon 1 to the rest of the phosphate group. Whoops. Sorry about that. So now let's switch gears and talk about the PDC, the pyruvate dehydrogenase complex. Pyruvate comes into the PDC as pyruvate, and two things happen to it. One, it is decarboxylated, so a carbon is lost as carbon dioxide. And what is left after that decarboxylation is called hydroxyethyl. Hydroxyethyl is an unstable molecule, and so it is linked to a coenzyme called TPP. So we make hydroxyethyl TPP. And this is step 1 of what happens in the PDC. Step 2 swaps hydroxyethyl. So we're going to move hydroxyethyl to lipoic acid, our second coenzyme in all of this. And that's step 2. Whoops. So hydroxyethyl is shifted from TPP to lipoic acid, and I'm just going to abbreviate that LA. The reason why we shift it to lipoic acid is because lipoic acid is going to steal electrons from hydroxyethyl. Lipoic acid as the coenzyme is going to be reduced and hydroxyethyl is going to be oxidized. The end result of that stealing of electrons is that hydroxyethyl actually becomes acetyl. And that acetyl is linked to lipoic acid. And I'm going to put a little R here to remind us that that is reduced lipoic acid. Step 3 is the shifting of acetyl from lipoic acid to CoA. And we've made acetyl-CoA. Now I told you that there are 5 steps to the pyruvate dehydrogenase complex, and we've made acetyl-CoA in 3. So it kind of leads us to wonder, well, what are the last 2 steps? The last 2 steps are for recycling the enzyme complex itself. We start this off with lipoic acid in its oxidized form. We ended with lipoic acid reduced. We can't have that. So lipoic acid has to be returned to its oxidized form. The way that we do that is in step 4. Now it's going to get a little messy. Step 4 is that lipoic acid reduced goes back to being lipoic acid because FAD takes those protons and electrons, and FAD is reduced. So FAD becomes FADH2, so that reduced lipoic acid can go back to being oxidized lipoic acid. The only problem is this FAD is stuck to the enzyme, so even it can't get the electrons out of there. So the final step, step 5, is that NAD then takes those electrons from FADH2. NAD goes to being in its reduced form, NADH plus H, and NADH plus H is going to shuttle those electrons on to the electron transport chain. So if we back up and kind of do it a little bit more of an overview sense, step 1 of the PDC is converting pyruvate, which is 3 carbons, into hydroxyethyl, which is 2 carbons, through the loss of a carbon dioxide, decarboxylation event. Step 2 is shifting hydroxyl from the coenzyme TPP to the coenzyme lipoic acid so that lipoic acid can oxidize hydroxyethyl to acetyl, accepting electrons and protons for it. Lipoic acid becomes reduced, and acetyl is the oxidized form of hydroxyethyl. Step 3 is shifting that acetyl to CoA so that we can create acetyl-CoA, the point of the PDC in the first place. But the enzyme needs to be recycled. So step 4 is absorbing the protons and electrons from lipoic acid, returning it to its oxidized form, and what's doing that electron absorption is FAD becoming reduced to FADH2. To get those electrons away from the PDC entirely, NAD has to come in as an electron shuttle in step 5 and take those electrons and protons off of FADH2, returning it to its oxidized form, and then NADH plus H, reduced, can go to the electron transport chain and drop those proton and electrons off. So that's what the PDC does. That's the level I expect you to know the PDC. Again, no enzyme names needed, just the step-by-step chemistry of how we get from pyruvate to acetyl-CoA and a completely recycled enzyme.